Hello everyone, we will start shortly when students arrive. Else we will discuss. Hello, Shrikant, you are here? Hello Shrikant. Hello, Shrikant. Okay, let's start the session because it's already a lot of time now. Maybe Shrikant is not able to hear us, but we will start. So we have already seen week 4 has as week 4 assignment has been seen. Now this is week 5 assignment. So in week 1, week not week 1, week 5, assignment 5, first question. Find the root of the characteristic polynomial equation in terms of z for MA process given below. So this is all EKs. These are the white noises at current time instant one step backward, two step backward. So it's a 3 point system for which you can see the solution. You can just take this Z as the current system, and then that's an operator you can apply, and using that you can find out the complex uh, roots. So these are the roots. B is the answer. It's very simple. You just have to assume as a sort of quadratic only, and that is possible. You just have to substitute. Take a Z transform. Is the process in question two invertible? So it is not question two. It is actually for question one. So is the process in question one invertible? So answer is yes, and the answer for it is that lies inside the unit circle. If it lies outside the unit circle, then it might not be invertible. And having a roots as complex does not matter. In that form, obviously you get complex root most of the time. Choose all correct statement about MA process where Q is finite. So you go only as a finite distance in finite steps forward. So apart from, I mean not apart from, all the answers are correct. So let's see one by one what are the answers. So it can be written in infinite order. Yes, obviously when you write coefficients might be negligible or zero, but yes, it all random processes, all of these processes can be written as function infinite order. But when we are trying to make it a realistic process, we have to come to a finite order and truncate it basically. The recovery process is a finite order process. Yes, so when you come to this thing, recovery processes, you use it for till finite order only. MA process is a stationary process. It's always a stationary process, it's not a non-stationary process. So you have a mean that lies in certain threshold. That is what it means. If two MA processes have the same ACF, autocorrelation function, one of them must be non-invertible. Because one MA process, one ACF maps to only one process. You cannot have two processes coming to same one ACF. That is invertible. Okay, consider the an ARMA 2-3 process. So let's say if this is your signal, random signal with all these white noises, which depends upon its internally, it's not independent of itself, but it depends on its own also. Then what is the answer? So it is invertible, it's stationary. That's a question. So invertibility does not affect whether it's depends upon itself or not, or it's independent of itself. And yes, for this process, it's stationary. That you can check through the same process as you have done this here in Z form, Z transform. Choose all correct statement about this. One second. Let me see. Okay, choose all correct statement about stationary AR process. So let us see what sir has to say. VK does depend on its path and linearly in nature. So when we talk about linear, no, all processes that we have considered are linear. So even this one, all VK that we have considered, even throughout the course, if I am not wrong, are linearly considered. That is why you are able to add or subtract in this form. White noises are being added. Otherwise, if it had been non-linear, it is not always consistent that you have to add all the white noises or the random signals. It is not necessary. You may be able to add in a non-linear system also, but it's not necessary. And that is why we just for simplicity, sir has chosen linear processes. So it has a unique parameterization for the impulse response coefficient. That is the correct answer. All rest are not correct. Let's see what sir has to say. So VK does depend on its path linearly. Also, it does not depend on past shocks EK linearly. So it depends upon its path. As you can see, for example, this is the case. So VK is depending upon its path and on white noises. White noise is sort of shocks that we are talking about. Shocks is sort of a type or class in white noises that one can use. It's quite possible that you may have a white noise that is random, but may not be a shock. It is a stationary only when the coefficient lie within the unit circle. Stationarity, as we have seen, invertibility depends upon if it's there in unit circle or not, but not stationarity. For stationary, the poles are to be within the unit circle, but not all coefficients. So only option A is correct. Only poles have to be checked, not everything. All coefficients is not the point. If the autocorrelation function values estimated at lag 1, 2, and 3 for air process, these are estimate coefficients of process in order D1, D2, D3. I mean, so you have to estimate the coefficients in order of D1, D2, D3. If there are acts 1, 2, and 3, these are the values of the lags. So let's open the solution. If lag 1, lag 2, lag 3 are these, a correlation coefficients of air process, you can use Ewell Walker equation to find out D1, D2, D3. You have to just inverse it and you will get the answers. So A is the answer. Given AR process, VK equals to EK. Now these are past and this is a white noise shock where EK is a normal distribution uh, with mean 0 and 1 as standard deviation. The parameterization of the impulse response coefficient HK in its convolution form is, let's see. Yes, sir. So you can take this is a process, multiply it by your EK input, you get the VK. So we can just take it now, have the Z transform. Now we can separate through partial fractions, and this is the answer. So which you can see here, HK can be written in this form. So your answer becomes A for this. I think someone. The relation between ACF and coefficients D2 of this random signal where EK is the with Gauss's normal distribution. So for this you just have to use that Yule Walker equation similar as you have done in previous question. Yeah. So even sir says that you just have to do that, form a matrix, and we can find out the answer. So D2 is first option. For the air process, time series given in week 5, question 9. So this is the data that has been given at the top. So for this database, estimate the PACF, partial autocorrelation function at lags 1, 2, and 3, and 4 by respective fitting of AR models. So D option comes the answer. We can see it's simply you just have to write this small model. We have to take one by one. We have to fit each lag, and you can find the answer. So I am here. If you have any questions, you can ask. Let's wait for the students. Okay, let us see some type of noises. This is something that I'm going to explain apart from what sir has explained. This sir has explained what are white noises. White noises are basically completely random noises that you can have no correlation being formed. There is no standard deviation, there is no mean. It's purely random and is independent of its past. But if you go to have, let's say, we search colors of noises. There are several type of. You can see there are several type of noises that comes into play. First is white noise. If you go to Wikipedia itself, you will be able to see a lot of noises examples they have given. So white noise, we have understood that it is basically your totally random process, or you can say there is equal probability of any specific frequency in spectral mode or in the in frequency mode, and in case of uh, time domain, or let's say a spatial domain, you have uh, I mean, equal probability of having anything. That is white noise. So you might remember in old times. I mean, most of the students right now have might have seen those old TVs that when you go, I mean, when there's no signal, there is sort of blank noise that come, and the screen becomes black, white, gray sort of mix, dot 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 dot. Let's say let me show you this is so in TVs this used to be sort of image that used to come. This one is white noise, also known as salt pepper noise, and this used to come. The color, the I mean not the color, but the sound of it is also very random. You can go and see here. That is sort of white noise where nothing can be interpreted. Pink noise is somewhat when you have at higher decibels lower probability, but at lower decibels you have higher probability of that coming into place, but still it is random. The amplitude reduces, but I mean, let's say if you talk about in case of uh, the intensity or the spectral power density, there is a decrease every decade, or let's say every decibel. So you have, so logarithmics are counted in decibels, and every decibel you have some sort of decrease. With the increase in decibels you have decrease of your noise, that amplitude, that is known as a pink noise. That's linear. Brownian noise, also known as red noise, is sort of which is actually related to walks. For the molecule, how when molecules are walking, you cannot predict where it will go. But there is something that the mean is zero. The position from it will start is zero. Similar comes to the place when the mean can be interpreted, but not how much increase or decrease in error would be. What would be the variance? That cannot be defined. Variance for Brownian noise is very large. as compared to mean. So it's sort of a flat, but mean is given as 0. Blue noise is the sort of a opposite of pink noise. There is an increase in power spectral density, and all of this is without any reason. Our noises comes when you do not have any reason for them. Otherwise, they are not noisy, but something that is of interest to you. But when things cannot be explained because of some specific unmeasured quantity or ununderstood phenomena, then it is known as noise. That is also noise. So, violet noise is similar to Brownian noise in sort of you can see the spectrum, but it is not defined from as the opposite of Brownian noise, because Brownian noise is sort of you have some specific uh, what say phenomena related to it. Whereas violet noise, you can see that due to diminished sensitivity of human ear or high frequency hiss and the ease with which white noise can be electronically differentiated, many early adaptations of tether to digital audio use violet noise as a tether signal. These noises are used to suppress other noises. That is the use they have told. But it is the noise that increases with frequency. Lastly, a gray noise where the noise is now. So this mean that is there where you have the downfall can be adjusted. So this noise can be corrected. And lastly, the velvet noise. Velvet noise is sort of a reverberation. When you have noise that reverberate to its own self, it resonates. Resonance and reverberation is different, but based upon how much intensity is there, it recursively superimposed on its own self. That is violet noise, not violet, velvet noise. Let's say, okay, one thing what you all can do is you just close your ears very tightly. But not now. Let me complete my statement. You can close your ears very tightly. You might heard something. Not might. You actually will hear something that you cannot explain. That is black noise. Black noise is something that comes from which is, I mean, there's nothing, but still there is something. I'm going into philosophy, just like say, but it comes when you have an absence of something. That is your black noise. Mathematically speaking, you may not see that wow, it's nothing, so obviously it's much more clean, but it is related to us reception, how we receive things. So there is obviously some background noise that remains, and it's in absence. You feel that there's something different. So your, let's say your ears have been matched to consider random noises or something for which you do not focus on to be background noise, and suddenly it's absent. There's nothing, completely nothing, and there's nothing with no pressure changes are happening. You will see that you will find if you focus you will be able to see some background, not background, but there's no noise. It's very complicated for me to explain, but that by closing your ears you can understand. Let's wait for some more time. Since there are no students, I guess we can end the session. But I would suggest students to come because in next class I will have started revision summary of all the sessions. Thank you.